Get ready to blast off into the incredible world of brain-computer interfaces. Neurocareers doing the impossible is taking you on a journey to meet the fearless pioneers pushing the boundaries of what's possible. In this special series, we'll be shining a spotlight on the nominees and winners of the International BCI Award, one of the biggest and most prestigious awards in the BCI world. You'll hear from BCI professionals as they share their revolutionary work and get a behind-the-scenes sneak peek at what it takes to be a winner. So, buckle up, grab a snack, and get ready to be amazed as we explore the impossible becoming a reality in the world of BCIs. But before we blast off, I want to give a big thanks to the co-host of this BCI Award edition on our podcast, Dr. Christoph Guger and GTech Medical Engineering. When I was a faculty member at the University of Cincinnati and Cincinnati Children's Hospital Medical Center, my team and I did some pretty amazing stuff for patients needing epilepsy surgery. We would put special sensors, also called grids, directly on their brain to prepare for surgery and create maps of their brain in a much faster and safer way than is usually done. It's called high gamma mapping, and it lets us figure out in just a few minutes the essential parts of the brain that need to be spared during surgery. Can you imagine? You can create a map of language, motor, and even mass processing in no time. It was the first time this innovative technology was used at Cincinnati Children's Hospital Medical Center. When I moved to Florida, I established the first functional brain mapping and BCI program at Florida Hospital. I continue to use high gamma mapping to help epilepsy patients avoid losing their ability to speak or move after surgery. But even cooler than that, I created brain-computer interface studies that let patients control things with their brain in real time. Our patients could even spell words with incredible speed by just using their brains. No hands involved. I also discovered that brain-computer interfaces could help patients move their chronically impaired hands or legs years after a stroke when not much else could help them. So, I started working with the faculty from Advent Health University to help these patients restore their ability to use their hands. I received special training for it, and it's still mind-blowing how cool it is. My favorite part of what I do is teaching. At my established Institute of Neuroapproaches, I've integrated all my experience and knowledge into a unique course on brain-computer interfaces. With graduate neurobiology students, we started with theory, and then I gave them the BCI equipment so they could have hands-on experience working with BCIs. It significantly improved the way students learn, and they absolutely love this practical part of learning how to use neurotechnology. And all of this was made possible thanks to GTech's awesome brain-computer interface technology. They have everything from high-tech up to 1024-channel EEG systems to wearables, tools for neurorehabilitation, such as the medical-grade system Recoverix, and educational kits with unicorn hybrid block for learning how to work with BCI technology. But the most important part is their support and care. I have enjoyed working and collaborating with Dr. Christoph Guger and GTEC employees for over 15 years, and I hope for many more successful years ahead. So, if you are interested in GTEC's brain-computer interfaces and neurotechnologies, check out their website at gtech.at. It's worth it. Dear Neurocareers podcast listeners, today we are continuing our BCI Award series, and we have an amazing guest that joining us today, Dr. Giacomo Valle. And Giacomo will talk about his study on Biomimetic BCI that conveys naturalistic touch sensations via peripheral nerve stimulation for bionic leg. So, welcome, Giacomo. It's a great pleasure to have you today on our podcast. And can you please briefly introduce yourself and let our listeners know where you are joining us from what part of the world?
Yeah. Thank you very much, Milena, for the very nice introduction and for inviting me here to talk about this study, neuroprosthetic and BCI. So I'm now recently be promoted as assistant professor. So now I'm physically in Sweden. I'm at Chalmers University of Technology, just starting to build my group and continues this type of research on bionics and BCI. I just completed my second postdoc at the University of Chicago with Professor Besmaya. And before, I was at ETH Zürich with Professor Stanisław Popovich, where I actually completed and performed the study that we submitted last year to the BCI Award.
Thank you so much. And we would be eager to learn all the steps of your career. We will go through them a little bit during our conversation. And can you also let our listeners know about your educational background? So what did you finish? What did you do to do this all amazing work that you're doing right now?
Yeah, sure. Thank you. So I started to approach this field when I studied biomedical engineering during my bachelor and master studies. I studied at University of Genoa in Italy, where I come from. And then I moved to Switzerland at the PFL, starting to work on bionic devices, in particular prosthetic arms, and hands connected directly with peripheral nerves. So this was my first experience with the aim of connecting the residual nervous system, in this case peripheral nerves, to prosthetic hands, sensorized, where we can actuate and provide back sensation. So that was specifically the new part of this project. And I did all my PhD on how to restore sensation, directly stimulating the nerves. So trying to encode different type of sensation complex using different strategies of stimulation, and then test together with fantastic patients this device in functional tasks in daily life as well. So in that period, I learned a lot about, how develop a prototype and use technology that then is interfaces directly with patients. So that is like useful for doing functional activities. And yeah, so I started to work a little bit on the coding part, on the software, and then also on the assessment. But then, of course, I work in a very multidisciplinary team of scientists. And then I moved to ETH, where I started to study more how to interface the lower leg, like the lower limb and the leg, in particular the leg nerves, and trying to recreate a similar bidirectional prosthesis for lower limb. And finally, when I moved to US, and I started to work with interfacing directly the brain with the same scope of sensory motor restoration.
So you kept one line of research throughout all this time, just from different angles you were approaching it, as I see.
Right.
And what helped you to stay with the same topic throughout, although you were changing institutions? Because very often it happens that we do different type of studies with different goals as we move from one place to another. So what helped you to stay with the topic?
Yeah, exactly. So it was not easy to, when I started, I immediately understood that this interfacing between the man and bionic devices, machine, computers was really like my interest, my passion, and in particular the sensory motor system, this complex relationship between touch and the motor system was very fascinating and for me like a very interesting point of interest, like point of view on restoration or like how to use neuroscience driven approaches and know about neuroscience to develop technology that can be useful for patients. So I said, okay, I want to really continue on this. And I found that the need of sensory restoration in combination with motor restoration is in common to many neurological disease and population of patients that needs this type of devices. And so I try to learn as much as possible about how to create a stable interface between the nervous system and the bionic devices, how to communicate, and in particular, try to be focused on somatosensation, so touch and proprioception. But of course, always looking at the motor counterpart because it's, of course, the other face of the same medal.
Thank you so much. Also, you mentioned that you knew this is your passion, this research. Why is that? What motivated you to really start working with this type of neural interfacing?
Yeah, this type of technology can really be beneficial for the patients. So it's really nice to work directly with them and to see how our technologies are impacting the life, the quality of life, or just emotionally the patients, no, because they can finally feel again for their arms, or they can control and do for us are simple actions, but for them are something really really important. And this is for sure like a big motivation, or like doing translational research, so something that can go directly to patients is very rewarding. But also at the same time, I feel that this technology can give us a unique window on the brain because we have the opportunity to study also basic mechanisms underlying like how our technology can really do, because we have electrodes implanted in directly into the nervous system in like in an intimate contact with the fibers, with the neurons responsible for this type of control and feedback. So we can unveil neuroscientific research and like mechanism behind the efficacy of the effects of our device. So I feel that this part of neuroscience is also very, very interesting, and we can learn much more about the nervous system. We can learn more about the mechanism, and then we can use this information for the design of our technology and see the benefit. This is also the idea of the biomimetic approach more in general, no, trying to study how the natural system is working, try to emulate and simulate how our evolution, years of evolution that creates this type of coding in our brain for that specific information. And so how to use and replicate and emulate this type of coding for our devices and see if this type of development can really improve the technology.
Thank you. And who are those patients that you can help with the technology that you are developing?
We have the opportunity to work with patients that are normally have a neurological condition affecting the sensory motor system. That can be like, for example, in this work, like patient with amputation, upper and lower limb. So in that case, we don't have the limb. We have to replace the limb with a robotic prosthesis and then connect the prosthesis to the residual part of the nervous system, in this case, the nerves. And then we need to provide the patient with direct control of the prosthesis and also a meaningful feedback, sensory feedback from the prosthetic device. But also, for example, people with spinal cord injury or paralysis or hand impairments, where you have, in that case, a lesion of, for example, the spinal cord that can be partial or complete. But then in that case, the information, we have the arm, but the information are not going anymore to activate the arm or from the arm back to the brain. So we can bypass the lesion and, for example, in that case, implant directly the electrodes into the brain, the sensory motor cortices, and then we can record the motor intention from the motor cortex to actuate an extracorporeal limb or a virtual arm in virtual reality, and send back information stimulating the sensory cortex in order to give back sensation. So at the end are patients suffering from a certain sensory motor impairment at different levels, but then that they need a very similar treatment in the sense they need to have back feelings about the direct control of the arm or the leg and back the sensations, so proprioceptive and tactile sensations.
Yes, and it's very understandable when we are trying to provide a motor control for those people who lost their limb or cannot move their limb. However, why do we care so much about restoring sensation? Can you talk about that?
Yeah, exactly. So this is a really a link that can, if we think about our natural sensory system, our natural control, this is we use different type of feedback, the visual feedback, tactile feedback, proprioceptive feedback. And so we integrate all this sensory information in order to have a very precise and dexterous control. And the somatosensation played a very, very important role in this dexterous behavior, in manipulation, for example, in coordination, example. This is simply you can think about if you are in a cold day and you have your hands that are cold, and you start to lose the sensations, then you want to pick something into your pocket or something. This is you're struggling because you can't really feel very well what you are touching. And so in that case, or vision, if you touch something and you don't have the sensation, you try with vision to compensate. But there are many examples of patients also where you can't really use your vision precisely do task of manipulation. So the somatosensory feedback is extracting a lot of information from the object that you are touching. Is extracting information about how much pressure you're putting on the object, so to regulate the force in order to, if you're grasping a glass of water, you with the correct amount of force and not crushing it. And at the same time, you feel all the edges, the relative motion of the object on the skin. And in very few milliseconds, you can extract this sensory information, the sensory features, and these are used to have a precise control, and this information are integrated in your sensory motor loop, and then you can correct the force or you can avoid to lose the contact with the object or predict where the object is going. So all these sensory features are fundamental for our motor control. And our, the largest org sense that we have is our touch, and is distributed on our skin that is deformed, and this spatiotemporal deformation is converted in neural signal, and this neural signal is containing all the information about the interaction of your body with the external environment.
Thank you so much for this detailed explanation. And what are the biggest challenges of providing that sensation back?
Yes, it's a very complex, as we said, since we have thousands of biological sensors in our hand, where we touch something, these neurons are activating, and then each of these neurons is sending a specific code. So we have thousands of fibers activated, and each of these fiber is encoding a certain type of information, is sending a message. So we have this huge package of information that is going from the periphery into the brain, passing through different stages where is processed, is separated, is segregated, is converged, and then we arrive to extract the meaningful features from this complex code, and then we interpret these features to understand exactly the interaction that we are doing with the objects. So the first challenge is understand the neural code of touch. So there is still a lot of to know, like many research in this direction where, in particular in the Besmaya lab when I was before, there is a lot of monkey research where that is fundamental because we can really understand how the brain is encoding sensory information. And this is very important because when the moment that you want artificially recreate the sense of touch, you need to know exactly which features are important for certain actions or how the brain is extracting from the electrical signal and the code of the fibers of the neurons the information that are needed for the action. And this is is fundamental. And you can think about, for example, if you're touching a texture or like passively receiving a texture on your fingertip, this texture is represented in a certain way in your brain. There is like a pattern of activation representing the texture that you're touching. But if I move this texture faster or slower on your fingertip, you still understand that that texture is related, for example, to genes or to a glass moving on your skin. And your pattern of activation in the brain is very different because of this different in speed or intensity. So there are a lot of features that are independent or dependent by some physical features of the stimulus, like speed, velocity, or shape. So all this like coding is fundamental to develop the new strategies. Then when you understand how the natural system is encoding information, the other difficult part, the other challenge is how to use electrical stimulation and the technology that we have available with a certain number of channels, with a certain physical properties and mechanism to interact in the same way and evoke what exactly you want into the nervous system, how to write and type your messages into the nervous system. And this is where a lot of neuroengineering research is going in order to create this functional and stable connection.
Thank you very much. And what is the conventional approach of writing those sensations into the nervous system? I would like to start with the conventional approaches so that we can see what is the difference between those and that naturalistic touch sensation that you're trying to convey.
Right, that's important, exactly. First of all, we need to think that the field of sensory restoration, there are a lot of studies also in the stimulating the visual cortex or for evoking phosphanes or cochlear implants, so for the other senses. But if we consider touch, we need to think that also both for peripheral and for central, the experiments in humans and the first trials in humans are pretty recent. So it's like 20 years ago for the brain, even less, not even 10 years ago, when the first paper came out where stimulating the brain and microstimulating the brain was possible to evoke reliably sensations and then maybe exploited in a prosthetic device. So of course, the approach was at the beginning, and they still, for some technology, a very simple approach that is functional is, of course, the best, or is something that can be, at least for the first trials, the best option. So the first phase in these trials are normally to characterize how the stimulation parameters are related to the perception. So what happens if I change the amplitude of my stimulation? What happens if I change the frequency of my stimulation? So increase, decrease. And then you normally change that and you see what the patient is reporting. And you can, in this way, create also a lot of study in animals and monkeys, but you can create a function and transfer function between your stimulation parameter space and the perceptual space. For example, higher is the amplitude of your stimulation, higher is the perceived intensity of your sensation. Or, for example, higher is the frequency, and also higher is the intensity, following like different trends. Like one is linear, one is more logarithmic, but you have this simple relationship that you can exploit then for your prosthetic device. So what you do is like to link the output of your pressure sensors, linearly map this with your stimulation amplitude in order to have a linear relationship with your perception. So in that case, any pressure, if you increase the pressure on the prosthetic finger, you will receive higher amplitude of stimulation, and so you have higher and more intense percept. So this is an example, a very simple encoding approach that was used and is still used for most of the neuroprosthetic devices available both for CNS and PNS that is working. But if we look how our natural system is encoding information, it's not using really this linear map with the mechanical pressure on your skin, or a skin deformation is not linearly mapped with your, electrical activation in your nerves, in your brain, but the pattern is more complex. Of course, now, at the beginning, these simple linear modulations were successful and able to provide a functional feedback. But then, more and more we discovered about, this interfacing, the effect of our stimulation, and more information we wanted to encode and we want to provide the patient with, more difficulties with simple approaches, and more difficulties to have a natural perception. And instead of having like some learning of the patient that is associating this stimulus with something that you want. But in the perfect scenario, what you want is to have a tactile sensation as the one that you normally perceive when you touch something from your hand, because your brain is encoding this tactile information in the most efficient way after many years of evolution, and arrive to encode this type of information like that. So, and that is something that motivated us to try to study better how the natural system is encoding information, and then trying to replicate and compare these biomimetic approaches with these conventional approaches using simple linear modulations.
Yes, that absolutely makes sense. So can you then define what is a biomimetic approach? Because you have even in the title of your studies, Biomimetic BCI, yes, that conveys naturalistic sound. So what is it?
The idea of biomimicry is that as much we resemble in our neuromodulation strategies the code of the natural touch and the natural touch coding, more information we can provide the patient with. And in particular, a more natural evoke activity will be evoked exactly by our stimulation. And this evoked pattern of activation can be more like interpretable for your brain. And then this can be beneficial in terms of naturalness of the perception and also functionality of the device. So this was the idea. So the biomimetic BCI is a BCI that is using for somatosensation, of course. So somatosensory BCI is trying to replicate exactly and emulate how the part of the brain or the part of the nerves in this case are encoding the sensor information. So you need to design and explore and use your space of stimulation parameters in a way to evoke a pattern of activation in the nervous system that is more similar to the natural one.
Yes, thank you so much. And now let's get to the aim of your study. What was your main goal that you wanted to accomplish in this study?
In this particular study, the goal was to explore if using this biomimetic stimulation, so use more biomimetic stimulation compared to traditionally or conventionally used neuromodulation strategy, you can encode more sensor information into the brain. And if this artificial touch could be perceived as more natural compared to the normally evoked artificial touch using traditional stimulations that we know have specific limitations in terms of quality of the sensation, and also to see if this maybe more natural feedback could be also be more functional, because this is something that a priori we can think that something that is more natural is also more functional, but we would not certainly, sure about this type of link. So we expected that something more natural would be also more functional, but this simple approach using neuromodulation were proved already that some functionality was possible also with non-biomimetic strategy. So these were the goals of the study. And for this reason, we developed this biomimetic BCI in patients with lower limb amputation. We explored that in this type of populations.
Thank you. And how many people were enrolled in your study?
Yeah, so there are 3 transfemoral amputees. So these patients had suffered by a traumatic leg injury and then amputation. So they were amputated above the knee, so transfemorally, and we implanted the tibial branch of the sciatic nerve. That is a mixed nerve, pretty big, like your pinky. And we implanted multiple time electrodes that are the transversal intrafascicular multichannel electrodes developed by Professor Stiglitz in Freiburg. So these are like polyamide electrodes, stretchable, and with multiple contacts. We have 14 contacts per electrode. And thanks to our studies in models and in animals, we understood how many electrodes were the optimal number of electrodes to implant for a specific nerve, big like that. And then we decided to implant 4 time electrodes in this nerve, interfacing so all these fibers that are normally innervating the lower leg and the bottom part of the foot. So all these like the calf and the sole of your foot. Indeed, when we stimulate from each of these electrical contacts, we evoke sensation directly perceived on the phantom leg and foot. And then starting from that, then we continue with this specific study.
Thank you so much. And now about the stimulation. So you were comparing the conventional type of stimulation versus the new, that biomimetic type, more naturalistic type. Can you describe what was the difference in the parameters of the stimulation? How those 2 different types of stimulation differed between each other?
So this is something that we are investigating both, as I said, using information from our animal experiments, where we can record directly at different stages of the nervous system the natural pattern of activation. And then we use also models, in-silico models, to emulate and try to recreate how the natural touch is encoding this information. In particular, in this study, we use a model called PutSim, that is like an evolution of TouchSim that was developed by Professor Besmaya in Chicago, and then this one was developed at ETH with Professor Raspopovich, where in this model is a model where it's possible to simulate any type of spatiotemporal deformation of the skin, in this case of the skin of your foot, and then since is recreating the correct number of mechanoreceptors, the distribution, how these mechanoreceptors are responding. These in-silico models are validated with microneurography data in humans and in animals. So the model is able to tell that if you touch in a certain part of the foot, how these fibers are firing naturally when you touch that specific part. So you can see how all these fibers are firing in the moment that you touch that specific area. So all this information can give us some ground truth, some information how to design our stimulation strategies, because what we want is to recreate that specific pattern of activation inside the nerve of the patient. So to do that, we did one step more. Before, to design the perfect stimulation strategy, we didn't go directly into patient. But we did a step in animals to understand exactly what happened when you change your stimulation trains from conventional to biomimetic. So in particular, what we understood, so in the moment that you touch your skin, there is, and if you record the spatiotemporal activity in your nerves or in your brain, you have a huge information coming during the transients. So when you press and release, there is this like bump of informations, and in the sustained phase. So if I press and stay and then release in the sustained phase, you don't have so much of activation. So you have a kind of a shape that is like bimodal, so in the sense that you have like the first peak, then you have a certain firing during the sustain, and then you have the second firing when you release. So the shape of your train is completely different compared to the linear, where instead, if you map linearly your pressure with the stimulation, as we said before, you have an increase intensity. Then you have in the sustained phase a lot of stimulation because it's the peak of pressure. And then when you release, your stimulation goes down. So if you think of that in the two train, the non-biomimetic train as low values, then the peak in the sustained phase, and then the release with, again, lower values. Instead, in the biomimetic, you have high activation, so higher firing rate, higher activation during the first transient, then decrease, and then again high when you release. So the temporal profile of your stimulation train is completely different. So what we did is to test in animals using we implant decerebrated cats in this case, where we implanted electrodes in the nerves, in the sciatic nerve, and then we stimulated and we recorded the activity in the dorsal root ganglion and in the spinal cord of the animals to see what happened at the pattern of activation when you stimulate with a stimulation that is biomimetic compared to something that is not biomimetic, and compared to natural touch. Because if you poke the animal leg, you can see the pattern of activation in the dorsal root and in the spinal cord. So we observe a certain pattern of activation, and when we stimulate with our biomimetic trains compared to the conventional, we saw a more similar pattern of activation compared with the natural touch respect to the non-biomimetic pattern. So this information about the transient is traveling into the nervous system, because you are injecting this information in the nerves, and then goes up in the spine. And then if you measure in the spine, this pattern of activation is still more similar to the natural touch. So this was one of the reasons that motivated us to see, okay, so if we are able to really to have a more natural evoked pattern of activation, we can maybe expect to evoke more natural sensation. And this is what happened then with the patients.
Thank you very much. And now let's talk about the patients. Can you maybe guide us into the study itself? Here are the patients. They came to your lab. If that was the setup, how did you convey this experiment with them? So if you can just guide you through this step so that we can imagine how all this was happening.
Sure. As we said, we enrolled 3 transfemoral amputees. We implanted these patients in the tibial branch of the sciatic nerve with these 4 electrodes. And then they started a clinical trial, a short-term clinical trial. So it was like 3 months each patient, implanted one after the other. And then, at the first thing that we do, since contrary to the cortex, where there is like an expected somatotopy of the tactile sensation going from the thumb to the ring finger, organized in a certain way in the homunculus, in the nerves, this is more complex because the fibers are mixed. The nerve was very proximal, so very, not close to the foot, but was like at the thigh level. So if you look at inside the nerve, all these fibers are mixed. So you don't know a priori the map of sensation that you can evoke. It's something that you have to do after the implant. So what we did is to stimulate channel per channel and see and ask to the participants to report where exactly the sensation was perceived, the quality of the sensation, the intensity of the sensation. So in this way, you can create what we call projected field map. So where you have, when you stimulate with this electrode, you can evoke a sensation in this specific area of the foot. And so you create what we call the personalized map of the sensation, because each patient is implanted in a maybe different way. The nerve is a little bit different. So each channel evoke a certain sensation. And this is fundamental to have, like, the overview about your artificial touch map that you can evoke. Starting from that, of course, one of the difficult, challenging part about sensations, but something that is very difficult to study in animals because they cannot tell you what exactly are perceiving, You need to do like psychophysical experiments to measure the sensations. In humans, you can directly ask them, right? But at the same time, the difficult thing is that our subjective, most of all, our subjective reports, very like descriptive, and as something that for me is pleasant, maybe for you is not, or painful for me, for other, there is a lot about experience, a lot about, memories and stuff. So you need to, first of all, you need to find some paradigm and some specific, measurement that can objectively quantify naturalness, because what is natural? What is a natural perception? This is not easy to describe, no? Because feeling a rock in your shoe is natural, but it's not pleasant, maybe, but it's natural. So, we had a lot of brainstorms about, what do we really want to achieve? We want to achieve something. We want to ask about pleasantness. We want to ask about naturalness, how to create that. And so we decided to do like a series of tasks where, in order to characterize the sensation in terms of quality, and using a lot different as many channels as possible with all the patients, in order to have a rich data set, enough statistical power. And then after that, there was the part of the functional part. So before going to the functional, in this phase of characterization, we decided to create different stimulation trains, in order that also for the patient was not easy to, pick one or the other, but have like a range of stimulations, not biomimetic, but also within the biomimetic, something that was replicating only one class of fibers, the entire population activity, subset of a population, in order to really see the implication of using some specific parameters compared to another one. So we did some task where we asked the subject to rate the naturalness of different type of sensations. We provide sensation in different locations. So sometimes the sensation was on the heel, or sometimes was in front of the foot, or sometimes. So we change also the locations of the sensation and everything. And the subject were completely blind of the type of stimulation. They just reported the level of naturalness of the perception. And so when we complete this experiment in the 3 patients, we observed that there was like similar response in terms of sensation. So in general, the biomimetic approaches were perceived and rated as more natural as compared to the conventional approaches, still not as a natural touch. So if you look at the scale, it's an improvement, but it's not yet like completely the same as natural touch. And this is like, something that we are still going in understanding how to make this more natural. But we observe a clear improvement of the perception. We also observe interesting things like some biomimetic approach using a specific feature was perceived as more natural only in some part of the foot. But in our foot, we have different distribution of mechanoreceptors. Sometimes are like more oriented in a certain part of the foot compared to the other. So this is also something that we are trying to investigating now. So like to understand what type really of information can be encoded, because also every part of your body has a different distribution of these mechanoreceptors. The skin is harder in some part of the foot compared to other, and so on. So we collected this data set that was very, very important for us, because in that way we could link perceptual experience with our stimulation parameter space, and then we had a more clear idea about how to design the neuroprosthetic. And so using that information, then we inform the design of our Biomimetic BCI, and then we test in the functional task.
Thank you so much. You also noted that there were similarities between all three patients. Did you notice also any differences between them? And if you did, what was the reason for those differences?
What was striking was the fact that even if, described in a different, sometimes in different way, or, rated a little bit differently according to, like, per subject, what we observed is in general that all the three subjects reported a more natural sensation using this type of stimulation, this frequency. In particular, we modulate the frequency of our stimulation, so emulating more the firing, the population, the aggregate population activity inside your nerve. But, the comparison, there were like maybe one patient was like rating everything a little bit lower, both the conventional and the biomimetic, some other patient a little bit higher. But the difference between conventional and biomimetic was significant for all the patients. Of course, the descriptors are different, but again, as I said, we try to measure naturalness as like the perception of something, regardless the singular description of the quality itself. If it was like touching, like poking or pulsating or vibrating, or there are a lot of different descriptors related to touch, that you can perceive many different types of sensation. But we try to ask the subject that, okay, is poking, but how natural is this poking? So imagine like having an electrical feeling, like if you hit with your elbow, the chair, and then you have this tingling sensation. This is for us like zero. It's like not it's natural if you want, because it's something that you can experience, but it's not what we want. We don't want to replicate that. We want to replicate the tactile feeling, no? So we said, okay, imagine that type of electric feeling is what we say, is zero, is unnatural. And then imagine to touch a surface or something touches your skin, that is like the natural touch, what we want to achieve. And in between that, you can have all the other perception, like pulsation, vibration, etc. But then all the subject had, in particular, this improvement in quality.
Yeah, thank you so much. And you also told that you still noticed that there was a difference from natural touch and the one evoked. Yes, even naturalistic type of stimulation. What do you think is the reason for the differences between, probably this is something you want to explore in the future to bring the current stimulation to more naturalistic. So what do you think were the differences, and where are you planning to go from here in your future studies?
This is something that we are trying to study and to investigate. The main barrier of our approach in general to restore sensation, both in the brain and in the peripheral nerves, is the fact that electrical stimulation is in general unselective, in the sense that you have like a group of neurons, a group of fibers, and when you stimulate, you activate hundreds, thousands of these fibers at the same time. And these fibers are maybe very different one to the other. There are some array or SA, or like able to extract and encode a different information. When you touch something and you measure the activation in the nerves or in the brain, as we said, each fiber is sending a specific message. But then when you stimulate with your electrodes, you can't really activate individually all these fibers. You can talk or write the message on each of these fibers. So a cluster of fiber is activated at the same time. So this is, for example, one of the reasons that we think we're not yet as a perfect touch, but still there is still some barrier. And of course, accordingly to what type of neurons, what type of fibers you're close to your electrodes, the quality of the sensation depends also by the type of fiber that you are activating, because there are studies we use microneurography or microstimulation where they characterize each fiber is encoding specific features, like constant pressure or vibration, etc. And, if you microstimulate that type of fiber, that fiber is evoking a sensation of pressure or a sensation of vibration, etc. But of course, if you activate a cluster of fiber that are mixed and they normally encode a different type of sensation all at once, the sensation perceived is a kind of paresthesia, is a kind of unspecific sensation. So, of course, as we said, in different parts of the foot, we have different cluster of fibers. So that can be maybe a factor where saying, okay, if I have close to my electrode certain type of fibers, I can evoke a sensation of this. If my cluster of fibers is very mixed selectivity, then when you stimulate, you have less natural. We are trying to understand that in terms of fiber organization, but also fiber functionality, as we said, because again, you have different type of mechanoreceptors. Every mechanoreceptor is also responding differently accordingly to the feature. So these transients are encoded a lot in the FA fibers and so the fast adaptive fibers. And for this reason, maybe, the message coming from that specific modality, from the array, the FA, is weighted more than the SA. So for that specific stimulus. So maybe, is a product of the number of fibers and the cluster plus the functionality and the importance of the feature that you are coding. So we are trying to explore that. And of course, as I anticipated before, only experiment in humans can give us this type of information. So the description of the sensation, the possibility to, have a complex experience of the stimulation that is described and directly perceived is much easier than train the monkey to do, task option A, option B, and then try to avoid any other type of bias that can be interpreted by the monkey as A or B. So we will see.
Yes, absolutely. And of course, we will follow your work and we welcome you at our podcast at any time when you have updates. My next question is, what was the feedback from your participants when they were able to have all those sensations which, previously were not available to them?
For sure, a very emotional moment in general is the part of the first sensations, when we stimulate the first time that the patient undergone the surgery, and then he's there waiting and say, okay, now we start. And then, they don't really know what to expect, what to feel. They don't, maybe some of them, they had an amputation many years before. And then finally they feel some sensation. It's similar to those videos of the cochlear implants, with the patients that finally can hear the voice of their wife or mom. And it is pretty emotional because they can say, oh, I finally feel again my leg. And last time that I felt my leg was before the accident, or like was like a pretty emotional. And of course, we try to, avoid as much as possible any type of bias. Since it's like subjective report, you want to say, what you are feeling, or like trying to, you need to give them also pre-reports of, tell me what you're feeling, anything. There is I don't expect to see anything. And, we observed that in general, this type of stimulation, they were able to perceive a difference, like something that, okay, this one, no, this one, yeah, this is like more natural. But I think the best was when we implemented this in the prosthetic leg, because when they worked with, we created this bionic leg that is a prosthetic device. This is a Ossure Rheoni. It is a semi-passive prosthesis, but we place a sensorized insole with pressure sensors under, and we assign in each of these sensors a specific electrode, a specific channel into the nerve, and we deliver the best, so the most natural pattern that the subject would describe as more natural. And in the moment that the subject did the first steps, say, oh, this is like, I feel very well, it's very pleasant, like I feel very well from the prosthesis. And then we ask the subject to do different type of tasks. So we ask to climb the stairs, ascending, descending, and also to do like a dual task where they are walking and at the same time they are spelling backwards some word, 5-letter words. So and in that case they need to walk and do another task, so their attention is on the other thing. And we measure the difference of having like a conventional approach compared to a biomimetic approach. And what was very interesting to see, and this is related to the point of functionality and naturalness, that we measure a clear improvement of the performances. So the subject was faster to climb the stairs that are normally challenging for patients with transfemoral amputation, was able to do this dual task better. So the mental accuracy was better because walking was a kind of more natural in the sense that, this information is more natural, so it is processed in an easier way by your brain, is interpreted easier. You don't need a cognitive step to understand, it's more interpretable. And so your cognitive resources are available to do other things, or you are better in the control. And in particular, the confidence in walking was boosted. And this is important because, patients with transfemoral amputation, they are afraid of walking. They always have to inspect the prosthesis. It's dangerous because if, they need to walk very carefully. But in the moment that they finally feel the leg and, they are more confident, they put more weight on the prosthesis, they walk in a more secure way. And then the functional benefit is also due to that, the fact that they are more confident. And I think the subjects, they appreciate that and they experience this type of feeling.
Very encouraging. Can you briefly summarize the results of your study?
In our study, we demonstrate that biomimetic stimulation based on in-silico model-based approach, we're able to evoke a more natural pattern of activation in animals compared to conventional approaches. Then we developed the first closed-loop biomimetic neuroprosthesis for lower limb amputees embedded with this biomimetic stimulation. And this biomimetic stimulation provided more natural sensations compared to conventional approaches. And then finally, this biomimetic feedback was exploited in functional tasks, demonstrating that a more natural feedback based on this biomimetic stimulation was able to improve the walking abilities, the mobility of the users, as well as their confidence in walking and reducing the cognitive load.
Thank you. Yes, and that question that you talked before at the beginning of our podcast, that does natural equal to better functionality, you also answered that question that actually it is. Yes.
Exactly. So this is points out in the direction of is reasonable, makes sense to develop biomimetic approaches, not only because is how the natural system is evoking is elegant or whatever, but is because there is a practical implication in terms of perception and also in terms of functionality. So these sensations are exactly integrated in your motor control in a more natural way as well.
Yes.
And we also explore this biomimetic stimulation with the brain, and this is something that we are doing right now. We conducted the studies in people with spinal cord injury with this bidirectional brain-computer interface, where we implanted the sensory motor cortices, and we try also there what was functional for PNS. We are now translating that for the CNS and stimulating directly the brain.
Very impressive. Of course, we will be looking for updates. My next question is, you mentioned at the beginning of our podcast that what motivates you is, of course, helping patients, helping all those people who need this, but it's also learning about the nervous system. It's a window, yes, into how our nervous system operates. So from that perspective, was there something that you learned about how our nervous system works, functions during the study as well, that maybe you think is worth mentioning here?
Here, I think there is a lot of, this is a very clear study, at least those that I performed in my career, where we use a lot of our neuroscientific understanding to develop this technology, because in here, we really use animal models to validate our approach and measuring and trying to quantify at the neural code level this possibility to evoke a more natural pattern, and then prove that in the translational way that when you go from animals to humans and you implement your discoveries, then this can provide benefit for humans. This was I think a very nice translational study in that aspect. We understood that it's possible to improve this sensation using these biomimetic strategies, even if our technologies may be still in the phase where we need more channel, we need maybe more implant, a better interface. There are some barriers and limitation of our electrical stimulations, but still using the existing technology and just shaping the parameters and the temporal informations, already these small steps are informative for our nervous system. The nervous system can interpret better the signal, and we can have a better efficacy of the device. We also are understanding in this case, for example, the topographical representation of the foot in the nerve, how the different fibers are responding to electrical stimulation. And so this is also very important. And, it's also very cool, in my opinion, to see how the brain is able to interpret an artificial signal, like an artificial touch, also integrating that in the other in the rest of the cognitive processes, like multisensory integration or sensory motor control, no? Because this is like an artificial signal that is coming from outside, that is completely artificial indeed. And then this is integrated with vision, with the rest, and then even if it's a more simplistic representation, is an impoverished representation of the natural touch, right? But still, with this small amount of information, the brain is able to extract all the things, the best things as possible, and then use that to have a better function. So this is also pretty interesting.
Yes, yeah, I agree. And that component is fascinating. Any input, even it's not the natural input of the system, but our brain still is able to integrate and interpret. And yeah, if you could summarize just several bullet points, what makes the artificial sensation to be perceived as natural in the human brain? What would be those main points, at least at this point in time? Yes, at this level of research that we have right now.
So for sure, what we've proven here is that if you recreate the aggregate population activity with your firing rate, so the rate code in the nerve, so the fact that you have this higher firing rate during the transient compared to the sustain, this seems to be already something that can improve the perception or the processing also of this perception. This is something that, for example, in the brain, we replicated, but instead of with the frequency, with the amplitude of stimulation. So again, in the brain, it's a completely different animal, no? Like you have a network of neurons, all interconnected, are not fibers, one close to the other. And this is propagating the message everywhere. But what we use is change amplitude with and if you look at your brain when you're poking your fingertip, you see a big activation, spatial activation. This information is expanding, then shrinking and expanding again, similarly to what is these two peaks of activation in the nerves. And at the population level, this transient versus sustain is very similar. in the brain and in the nerves. So we also tried that in the brain, modulating the amplitude, like having peaks during the transient, then reduce and peak again. And also in that case, we proved that we were able to provide a better, like a more sensitive feedback, a more precise feedback to people with this type of implants. Actually, was there with Charles Greenspan is the other BCI award, like the third place on that, where exactly we used a similar idea of translating from the biomimetic periphery to the brain. And also there we were able to improve the perception, showing that, these like basic features are working both for the peripheral nerves and also for the brain.
Yes, thank you. And what was the biggest challenge for you in this project, and how did you solve it?
This is a good question. Difficult to say the biggest. For sure, like quantify the naturalness in terms of experimental procedure, the quantification of the naturalness and trying to avoid any type of bias of, intensity or like, anything was a lot of work. Then, of course, like implement everything in real time is always like a challenge. One thing is like to stimulate and that's it. The other is like to make reliable feedback in real time while the patient is walking around, do stuff where there is a lot of, mechanical stress on your electrodes. A lot of things are changing when you're moving and you don't know exactly. So a lot of work in terms of the implementation itself. But yeah, of course, I didn't really participate the animal experiments, but also the animal experience was like very, very tough and long. But this is like something that, as I said, it's much easier to ask directly the patient how did they feel. But the other thing is like to create all the setup for the animal. And in this case, there was not training, but still the surgery was very long. A lot of electrodes implanted at different level of the nervous system. So pretty challenging.
And what was the most unexpected result of the study for you? Because usually we have some expectations, but very often we also get something that we didn't expect that surprises us. Maybe there was something. Mm-hmm.
Yeah. No, for sure. When we tested different stimulation paradigms, and so the subject reported all biomimetic strategy were perceived more natural than non-biomimetic. But I expected that, the aggregate population, so the full biomimetic approach was maybe like, the best way to stimulate. But then we found this like different part of the foot, the subject had different preferences accordingly to the locations. And also this was like consistent with the patient. So this was pretty like interesting because, that means that exactly the code that you are sending and the fibers that you are interfacing with are really, bringing some information. And if you don't speak exactly the language of those fibers, these are like more difficult to interpret or maybe easier. So that is a kind of unexpected, interesting result that is like pushing us now to characterize better. Of course, we want to try to find some general principles and mechanisms that then we can apply to the different patients and try to generalize exactly our approach. But the personalization and the fact that, how much segregated is the information, how much of the specific information we need to convey, this is like making more complex and complex, the approach in general. But I think that, we need to take in consideration all these aspects in order then to have finally a very good interface.
How do you see that ideal, perfect neuroprosthesis, let's say prosthetic leg, that provides both motor function and sensory feedback? That's the first question. And second, what is still missing from that ideal picture that we want to have?
There are a lot of discussions on that. I feel that we are still like, there is a lot to do. As we saw here, the sensations are a bit more natural, but still not super natural. And all, if you think about the multidimensionality of the tactile experience when you touch something, all the edges, motion, curvature, shape, and things that you perceive, this is like nothing compared to that. So we still need to, complete and go more in depth with the experience of touch and explore how to do that. Another important missing part is for sure proprioception. For example, with the hand, there is like a phenomenon called stereognosis where you integrate the tactile and proprioceptive information in order to perceive the shape of something that you're touching. So the conformation of your hand on an object plus the contacts of the force and everything that you are perceiving from your fingertip are integrated together in order to have like this experience, complex experience about what you are touching. So the proprioceptive information, of course, you can understand the shape maybe only from the contact, but the conformation of your hand is fundamental for exact information. So the same for walking or for the leg, we try to do a kind of proprioception in our study, but still with electrical stimulation, it's not very clear how to evoke direct proprioception. It's not possible when you stimulate the nerves, difficult when you stimulate the muscle, not really clear when you stimulate the brain. So it's a big open question that needs to be addressed with the goal of having a complete sensory restoration. And of course, the motor, I'm not an expert on the motor side, but there is always a discussion with all the neuroscientists and neuroengineers working on that side because sensory motor are related a lot. So for the brain, there is this complexity of extracting the kinematics and neural activity related to the motor intention from the brain. And for the nerves, it's also very difficult to extract the neural information directly from the nerves. The signals are very weak. And still, there are some approaches tested mostly offline, not really like real time, trying to decode motor information directly from the nerves. But for prosthesis, I think the approach is exploiting the muscles. The activity of the pattern of activation in the muscles is for sure the best strategy right now. Maybe implanting electrodes directly in the belly of the muscle, or compared to the nerves. And for the upper limb, there are many groups working on that, also on the lower limb. But for the motor, also there is still a lot to do. If we think that there is a cybathlons, I don't know if you know this competition for people with disability and technology, and there is all like is a race for people with different type of disability that they can use any type of prosthesis or technology, to accomplish tasks of everyday life. So not really like complex things, but simple things of daily routine. And still, the simple prosthesis like hooks or very, very simple body power prosthesis are still performing better than the super sophisticated control of maybe sophisticated hands. And this is like a thing that we need to consider, because that means that we are still also far on the motor side to replicate and try to be dexterous as the dexterity of the human hand. Now, of course, the tactile component we think it's a very fundamental, but also the algorithms are still struggling to reach the same capability. But adding the sensory parts and maybe proprioception in the future can maybe make all this more closer to the flexible dexterous behavior of humans.
Yes, thank you very much. And then my next question is that actually people are often asking is about the comparison of what we have right now with the neuroprosthetics and the possible transplants, because as I know, that area is also developing and there are hand transplants. There were even, I think, bilateral, both hands were transplanted. So what are advantages and disadvantages of those two fields? And maybe there is some intersection between them that in the future can be explored and used to help people.
Yes, no, absolutely. I think is it's a very complementary and related field of research. And I agree that the integration of novel surgical approaches and neurotechnology can be very successful and useful for this implementation. We saw something with the osseointegration, with the reinnervation in the muscle, the target muscle innervation or sensory reinnervation, RPNI, the AMI by Professor Huger at MIT. So there are many surgical approaches combining with technology that are effective or showing a lot of benefits of using that. Transplant per se, I see two main problems, but of course, the research is evolving, so they are working on that as well. One is the fact that that they have immunoresponse for the entire life, so they need to take drugs for that in order to avoid any rejection and etc. So that can be for sure problematic for those patients, and also the fact that the psychological effects of having hands that are not yours, like having different color, different shape, is something that, with your hand, you express also, effective touch and, you touch others and you interact with people. And having different hands, there are studies showing that psychological effects are sometimes pretty heavy. But apart of that, I feel that it's absolutely a field of important research. I don't know much about the legs because of the stress of the weight and etc. But for sure, for the hands, there are a lot of videos of patients that they recover a lot. In theory, we think that with bionics and maybe exactly with a combination of surgical approaches, we can achieve better results in terms of that. One recent paper about biomimetic leg prosthesis by Professor Huger showing that using this AMI, agonistic-antagonistic connection of the muscle and interface, can restore a very biomimetic control. So there is the patient with crossed legs like this while speaking and moving the foot, very in a natural situation. So very, very impressive and better gait in general for every participant. So I think, and that is surgery plus technology.
Yes, it would be very interesting to see what is coming up from this integration. And you mentioned many things that still need to be done in order for people to have that ideal device that provides both functionalities and sensory and motor. And I'm sure that many people who are listening to our podcast might think about getting into this field and contributing to answering those questions. So what would be your recommendation for those people, how to get into this specific field? What skills do they need to have? What's the best approach to get into this area?
So the one important piece of advice, I think, is try to be really open-minded and open to, be creative because I feel that, to arrive at this type of man-machine interfacing, etc., we need a lot of smart ideas to how to do that in the best way, in an optimal way. Of course, the field is growing with companies and research groups, and I feel that there is the need of very diverse and multidisciplinary teams because we are talking about topics that are touching mechanical engineering, robotics, neurophysiology, neuroscience. So there is a lot of intersection of psychology, between fields of research. So I feel that, that different background can participate in this type of research and that contribute to this aim. And accordingly to what exactly is the part of this human-machine interfacing is interesting, you at most, if you're you're fascinated by the robotic part, by the fact to use robots that can interact with environment and be controlled in a more natural way. If you're more about the mechanisms and how the brain and the neuroscience behind, or the cognitive aspect of having something artificial attached to your body that is like perceived as a natural limb. So there are so many different aspects, and I feel this is good because even if you are coming from a different background, you can bring your contribution and your valuable insights to help in the development of this new generation of neuroprosthetic devices.
And as you are now a faculty, obviously you will be looking for people to work with you. What is your criteria for selecting the right candidate to work in this field? What are you looking for in potential candidates?
So for sure, we mentioned this multiple times. I think passion is the passion-driven people. I really like to work with people that are really passionate for the topic, because I feel that in general, in research and this field can happen that sometimes you have like dark moments where nothing really works, and you spend a lot of time. And I feel that if you have the motivation and the passion, can really drive, and perseverate and continue on that thing. Of course, this is a very, very valuable skill. Also, since it's so multidisciplinary, you need to study a lot. So if you really like to also to spend time in studying, it's not only development, I feel. It's a lot of studying and reading and, modeling, brainstorm. These are very crucial moments to really understand the basis of what we are doing. And of course, the teamwork. So it's not something that you can do alone, with your computer in a room. But here we work with patients, we talk with patients, we involve them in the design of what we are doing because we need the feedback from them. And we collaborate with a lot of people in order to make this is a reality, So I feel these three, like teamwork, passion, and then motivation of studying and reading are really things that are looking for, because I feel that the other skills are you can learn if you are motivated to study and passionate for the field. You can learn also new code language or whatever, like how to program the robots. You can stay without problem. And of course, I have a master thesis open and PhD positions. And so if the people are interested in that, they can contact me, and we can see if we can expand the group. And this is something that I'm trying to do right now.
Absolutely. And we also will add this information into our podcast notes. So for those who are interested, they can contact you. So that's a perfect opportunity. So thank you for mentioning this. And the last questions I would like to ask about the BCI Award submission. Maybe you have some suggestions for those who are going to submit their study for the BCI Award. What would be your recommendations? What would you recommend to focus on or to emphasize? What would be the best approach?
It's a very nice opportunity. It's something that motivates us also, to innovate. And so I feel that the creative part is something that is important, and to have hypothesis-driven solutions, something that, if you proceed in that direction and you are proposing or you tested or you are applying for a new method, a new technology, I feel that if you clarify well the hypothesis behind why you decided to do that, and the creativity and the novelty behind the innovation, is something that can be very valuable and appreciated, because they can also, people that are maybe not exactly in your field, but are in the field of BCI, can understand the motivation behind the hypothesis and how your study then is answering with novel result, novel findings, the hypothesis that you have at the beginning. I feel like a kind of story that is open and then closed at the end is something that can be useful for this specific application.
Thank you so much. And maybe there is something, a question that I haven't asked you yet, but you would like to answer, maybe something that was left that we didn't touch upon and you think that it's important. So it's a good time to do this.
Yeah. Oh, I think we touched everything. We also mentioned the thing about the brain. So I feel that we described the study well. We contextualize the study, and we will submit also next year.
Okay.
Actually, this year.
This year
we have a study for this year. So this is the second time that I sent. It was in 2020, and then we sent twice two applications, one for the brain and one for the DNS. But we have something for this year.
For this year. Very good, very good. We will be looking forward to your submission. And I think it's another motivation for our listeners to submit because they see that you already submitted and want to submit again. So there is a value in doing these submissions. So
yes.
Exactly. Thank you very much, Giacomo. The last thing you want to tell to our listeners, any piece of advice? We have many people that are trying to pursue their career in neurotechnology. So anything you want to mention before we end our podcast?
No, just continue to be creative and innovate and be open-minded and with the ideas of other people, discuss a lot, fight a lot as well. And this is something that I really like. I mean, it's motivating me to in this type of research. It's very nice to work with brilliant people, very smart, and have nice conversations about, these problems, how to solve these problems. It's very, very inspiring. And everybody, I think, can contribute and can can make the difference.
Thank you so much. Of course, I wish you all possible success in your future studies. Looking forward to the updates. And thank you very much for being with us today. It was a great pleasure to speak to you. So thank you.
Thank you, Milena. Thank you very much again for the invitation.
Yeah, great pleasure. Thank you.
Are you a fearless pioneer in the world of brain-computer interfaces? Do you have an amazing project that's pushing the boundaries of what's possible? Then we want to hear from you. The International BCI Award is one of the biggest and most prestigious awards in the BCI world, and the deadline for submission is September 1st. But don't worry, you don't need a top-notch budget or equipment to be a nominee or a winner. All it takes is a great idea and the determination to make the impossible possible. So, submit your project now at bci-award.com or find a link in our podcast notes and join us on this incredible journey to explore the world of BCIs. And make sure to listen to our upcoming BCI Award Neurocareers podcast series for tips and tricks on creating a successful submission. Who knows? You might be the next nominee or winner of the International BCI Award and proudly showcase your nomination on your resume to impress potential employers and establish a successful career in neurotechnologies. But don't stop there. If you are looking for more guidance on succeeding in Neurocareers, book a free consultation with me, your podcast host, Dr. K, at the Institute of Neuro Approaches. So, what are you waiting for? Let's make the impossible possible together.